So we are trying to figure out the scattering cross section of this very process. I mean the neutron proton scattering at low energies, and the so we have this kind of potential. It's an attractive potential for R less than A, which is 0 or greater than A. Okay? So it's a three-dimensional well. This is your well. So this is the R. Okay. So it is V of R. So this is 0 and this is minus V. Clear? Got it? So it's a three-dimensional well. Yesterday we have now by simple calculations we have seen we'll be considering only the S-wave scattering. Yeah? Okay, since we have this low energy scattering. Okay, so we'll consider only L equal to 0, that is S-wave scattering. We'll not be doing any high energy business here. Okay. So what we have to do? We have to look for, okay, so now let's look at the total scattering cross section first. So total scattering cross section is equal to 4 pi by K. Is it K square or K? K square summation of L equal to 0 to infinity 12 plus 1 sine square. That's right. Clear? Okay. So since we are considering only the low energy scattering, so we'll be considering, okay, for our process, for this process, so we'll be considering L equal to 0, we define delta L equal to 0 as delta. Clear? Got it? Because it will be delta L equal to 0. So that I will call as delta. How many terms will be contributing from here? Only one term. Okay, so I will be having sigma total is equal to 4 pi by A square 2L plus 1. L is equal to 0. It will be 1 sine square delta L equal to 0. That I write like this thing. 4 by K square sine square delta. Clear? So what we need to figure out? So this is our total scattering cross section. Clear? So what is an unknown quantity here? It's a phase shift. We need to figure out the phase shift. Let's try to figure out the phase shift. Okay. For that matter, we have to solve Schrodinger equation explicitly. Clear? Okay. So we'll go to the region. We have to only look at the radial. Since this phase we have seen, it comes with the radial part of the wave function. Clear? Because if you remember, when we tried to expand, when we had done the partial wave expansion of a plane wave, clear? We wrote the radial wave function in terms of the spherical Bessel functions. Clear? And in that, when we look at the asymptotic limit of the spherical Bessel function, okay, so we introduced an arbitrary phase delta. Clear? Got it? So that means for a given problem, if you need to figure out what is the phase, okay, since we have to look only the radial part of the wave function. Sorry, radial part of the Schrodinger equation. Okay, and the radial part of the Schrodinger equation. Okay, so let me write it. So radial part. So it's like this thing, dul. Let me write it completely first. So by R2, then you are having twice m by h square e. Is it? Is that true? So then it will be some minus v of r. Minus v of r. Potential, right? Okay, then you are having minus L into L plus 1 divided by h square r square. Sorry, only r square, huh? Okay, like this thing. So u L is equal to 0. Got it? So this is a radial part of the Schrodinger equation in terms of the potential and the angular momentum. Since L is equal to 0 here, clear? Okay, so let's go to our problem. Okay, so I will consider region. So in the region, R less than E. Okay, so what is our Schrodinger equation? Now, du, okay, by dr2. I will not use L. L is equal to 0. Clear? Okay, so plus twice m by h cross square. Okay, so E. Okay, so what is V of R? It's minus V naught. So it will be simply V naught U is equal to 0. So if you see, it is simply a one-dimensional equation. Clear? Everybody? Okay. So let me define now our k square is equal to twice me by h cross square, and k naught square I will define as twice m v naught by h cross square. Okay, so if you see, it is k square plus k naught square, and I will define some k1 square as k square plus k1. So it is simply this thing. So this is simply what? K1 square. Got it? So yes? Any problem? Okay, so what I am having? So it is d plus k1 square u is equal to 0. Okay. Got it? Clear? Okay. So now what is the solution of this very equation? So it's simply one-dimensional equation, one-dimensional differential equation. What is the solution? Okay. So u of r, okay. So u of r will be simply a. So let me write sine of k1r plus b cosine of k1r. Okay. You can write as e raised for I k1r plus e raised for minus ik, so that you can put in terms of sine and cos. But here is a boundary condition. What is the boundary condition? At r equal to 0, wave function must vanish. Okay, so our boundary condition is, so at r equal to 0, u r equal to 0 is equal to 0. So it implies then b has to be equal to 0. Clear? Got it? So what is our solution now? U of r is equal to sine of k1r. So call this as first. Now let's go to the which region? R greater than a. Okay? So when I am having r greater than a, since v is not there, it is 0. So what is our equation? So r greater than a, our equation is d2u by dr2 plus it will be simply k square u equal to 0. Because k naught is not there. Okay, so what is the solution? Now solution you can write simply as, so let me write here the solution as v, to differentiate between u and v. So let me write solution as v. So I'll write this v of r is equal to some, let's say c sine of, it will be the same thing because you are having the same equation. Okay, so let me write it as kr, and now since I am in the domain r greater than a, clear? So I'll introduce a phase. So that means inside the potential you don't incorporate a phase, outside the potential you incorporate a phase. Got it? So this is a general trick to solve a given problem. Now you have incorporated a phase which is unknown to us. Clear? Okay. So let's call it a second. Now how to determine this phase? Okay? Everybody? Okay, how to do it? So since I have to look, now wave function have to be continuous at the boundary. Is it where? At r is equal to a. So I have calculated the wave function here, is it? So this should be continuous at r is equal to a. And the first derivative should be continuous. Clear? So let's use the boundary condition. Okay? Wave function is continuous at r is equal to a. So what does that mean? U of a is equal to v of a, which implies, now let's write, so it is simply a sine of k1a is equal to b sine of ka plus delta. Call this as third. Okay? So now the first derivative of the wave function have to be continuous because you are having only a finite discontinuity in the potential. It is not an infinite potential. So wave function, this is the first derivative. Okay, first derivative of wave function has to be continuous at r is equal to a. What does that mean? Let's take the differentiation of this. So let's take differentiation. So it is k1a cosine of k1a. Clear? So differentiation. Sign differentiation is what? Cos of k. Okay, k1 r and k1, and r is equal to a. So here it will be c k cosine of, okay, k a. Let's call this is 4. Okay, so divide third by 4. Okay, so that you can eliminate a and b. A and sorry, it is c. It's c. It's not. It's c. So just divide third by 4. Okay. So it will help us to eliminate these constants. Okay. So divide third by 4. So what does it mean? So LHS. So it is simply tan of K1A is equal to tan of KA plus delta, and here is 1 by K1 here, and here it is 1 by. Clear? Got it? Now, so since we are in the low energy domain, clear? Okay. So if you are in the low energy domain, what is the value of Ka? It's small. Clear? So that means the argument here is very smaller. So I can use, since Ka is very less than 1, okay, so which implies I can always write this tan of x equal to actually sine of x. So that's equal to this. Clear? So what does it mean? So it means 1 by K1 tan of K1A is equal to 1 by K. So this I can put K plus delta. So what that is equal to? Now it is A plus delta by. Got it? So now what is our delta by K? So it's equal to 1 by. Okay, so it is this term minus A. So I can write it as simply tan of K1A minus K1A divided by K1. Clear? Clear? So what we have figured out? A phase. Is it? A phase shift we have figured out. So what is our this sigma total? So it is like this in 4 pi by k square. That is actually delta square by k square. So how much is that? 4 pi by. So it is simply equal to tan of K1A minus K1A divided by K1 whole square. So this is our total scattering cross section. Okay, so we can evaluate, we can figure out numerically what are the values. So it's of the order of Fermi. Okay, 10 raised to minus 15. So that gives actually the typical nuclear cross section. Okay, so this cross section sometimes represents you the strength of the interaction. Okay, how strong an interaction is. Okay, so now if you see this K1, okay, K1 square is equal to this K0 square plus K square. Clear? Is it? So what does it mean? So, or it means like this thing. K1A whole square is equal to, I am just multiplying it by A square. So it is K0 A whole square plus KA whole square. Got it? Just multiplying A square throughout. So it means, since Ka is very small, K is small, it means this K1A square is approximately equal to K0 A square. Since Ka square is very less than, it is actually smaller than K0 A. Got it? So that means I can replace this K1A, so which implies the sigma total is equal to 4 pi by, okay, K1. Okay, so this K1, how you write? So it's something K0 square kind of thing. Okay. Okay, so you can write it as A square here and A here. Got it? So that it will be simply equal to K0 square. Okay, so then you are having this tan of K0 A minus K0 A whole square. So now low energy, if you see in the low energy domain, the scattering cross section is independent of the incident energy. So incident energy is contained in this K square. K square is twice ME by H cross square. And this K0 is twice m v naught by h cross square. Got it? So you are having total scattering cross section independent of the incident energy of the particle, because we are looking only at the low energy domain. Got it? Clear? Now there is a problem. This formula cannot be applied when this term vanishes. So there, when this can vanish, at what values? Okay, when this term is out to be of the order of k naught a. Okay, so in that case, so when this k naught is again small, then this cannot be actually applied. So I will take this. It gives us to as the condition of the resonance, a bound state kind of thing. So that I will take later on. Okay. So what is the units of this scattering cross section? Meter square. So bar, na? Okay. So what is the unit of k naught? Inverse meter, is it? So k naught square is inverse meter square. So when it goes here, it is meter square. So you should identify your dimensions of a given quantity as well, whether your formula is correct or not. Okay. So clear? Okay. So let's take another example. Okay, by the way, have you done scattering in classical mechanics? At any level? Really? Huh? Oh, collisions. Okay, suppose if you are having a hard sphere hitting the another hard sphere, what is the differential cross section? So let me teach you later on. Because we need actually classical values are very helpful in understanding these values. Huh? So let's take another example. Okay, I will go to that later in the supplementary lecture. Okay, because they are very useful. So let's take example number 2. So let's take you are having a scattering of there are delta function. Okay, so let me consider a delta function v of r. So it's a 3-dimensional 3D delta function. Okay, so let's write some gamma delta r minus a, where gamma is the strength of the potential. Strength of potential. Okay, so I could have put alpha because we can use alpha. There is no problem. Okay, got it? Or let's use v naught. Let's use v naught. Why? Let's use v naught. Okay, let's use v naught. Okay, so what is our problem now? So it is something you are having a delta function. So it's a 3-dimensional delta function. Okay, it's a spherical kind thing. At r equal to a, you can think of a sphere. Okay, of radius, let's say r. But at a point r is equal to a, at a distance of r is equal to a, you are having a delta function. Okay, infinite wall. Okay. So this is our delta r minus a. Okay, so this is r, this is your VR. Okay. So now we are having two regions here. Okay. So I am having r less than a, r greater than a. So since I am considering the low energy scattering, so we consider low energy scattering. Okay, so implies I have to consider what? SV. Got it? Now what I have to do? So r less than a, I need to solve the Schrodinger equation. What is the Schrodinger equation? Since for SV scattering L is equal to 0, so the angular momentum will not contribute. And now the potential in r less than a is 0. Got it? So there is no potential term at all. So what I have? D2. Okay. d2u by dr2 plus k square u is equal to 0. Now what is the solution? So u of r is equal to simply a sine of kr. To satisfy boundary condition at r equal to 0, look here, it is not just a line, it's a sphere, huh? Got it? So sure, it's a spherical potential, huh? That's why this r equal to r less than a will correspond to the interior domain, huh? Okay, so for r greater than a, what I am having, the same equation, okay, plus k. Okay, so let me write v, huh? E square v equal to 0. What will be now v of r? So for outside domain, you simply introduce some sine of kr plus delta. So this is the prescription, eh? So inside domain you don't put what? A delta. Only for the external domain you put a delta. Got it? Okay. So now what I have to do? Okay. Just tell me. I have to match the boundary conditions. Okay, so the first boundary is what? Okay, psi must be, wave function is continuous. This is wave function is continuous at r is equal to a. Okay, so what does that mean? So it means a sine of ka equal to b sine of ka plus delta. Got it? Let's call this as first. Now what is the another boundary condition? First derivative is no, it's a delta function. Delta function has a infinite. Okay, r equal to a, it is infinite. That means when potential in a certain region becomes infinite, you use the first derivative is discontinuous at that point. Okay, so let's do it. So let's calculate it. Okay. So what is our Schrodinger equation? Okay, so let me write it this way. So let me put at r equal to a. Okay, so let's write the Schrodinger equation first. d2u, okay, dr2 plus, okay, so you are having this twice m by h cross square e minus v of r, okay, u is equal to 0. Clear? So let's write it. So I am having d2u by dr2 plus, so it is something k square u is equal to minus twice, okay, so it is plus twice m by h cross square. What is v of r? V of r is v naught. V naught delta r minus a u. Clear? So it's our equation, simple Schrodinger equation. Now I have to look at which point? At point r equal to a. Got it? So if you see at r equal to a, it is an infinite quantity on this side. Okay, so what I will do, I will simply integrate this thing. Okay, so let's integrate this thing. So you are okay, so let me take something, limit of epsilon tends to 0. So integrate something a minus epsilon to a plus epsilon over r dr. So you are having d2u dr2 plus k square ur. So that's equal to twice m v naught. These are the constant extra square. So a minus epsilon to a plus epsilon. Okay, delta of r minus a u of r and you are having dr. Clear? So I simply integrated it in which domain? In the neighborhood of r equal to a. Okay, so let's first integrate this thing. Okay, so let's integrate it. What it will give me? So you are having limit of epsilon tends to 0. So it is 0 plus. Okay, so what is the integration of d2u by dr? So it is simply du by dr. So evaluated at first term will be at a plus epsilon. Another term will be where? A minus epsilon. Got it? So this is the integration of this term plus. Okay, so what is the, since u is continuous, clear? Okay, got it? So since u is a, okay, so let me write it. So you are having limit of epsilon tends to 0. Okay, so a minus epsilon, a plus epsilon, k square u dr. So this is equal to twice mv naught by h cross square. Now look here. So you are having a minus f. Okay, so it's minus epsilon to plus epsilon. So that means this point is contained in the domain r equal to a. Clear? So when you integrate it over, so it will be simply u of a. So otherwise, if this a is not contained in the domain, it will be 0. So it will be simply u of a. Okay. So now look here. So you can take k square out. So it is integration of u, because epsilon. So when you take epsilon tends to 0, so it will be simply a to a. Got it? So u is a continuous at a at r is equal to a. So that means this term will be equal to 0. Samajh aa? So you can write, let's say it is something another function. Integration of u is some another function. Let's say f. So because f is continuous at r equal to a, so it will be f evaluated at epsilon minus f evaluated at minus epsilon. Both values are same. It's equal to 0. Got it? So what you have got? So you have got actually a discontinuity. Yeah? So it means, so you are having like this thing. So let me write delta as like this thing. So it is twice mv naught by h cross square. So you are a. So that means if you are having a singularity somewhere in the potential region where the potential is defined, then the first derivative is always discontinuous. Okay. So this delta means this object. Okay. So let's take it now. Okay. So now I will write it this. Du by dr is discontinuous, or d psi I will write d psi by d is discontinuous at r is equal to, in this case. So now tell me what is the amount of discontinuity. So I have to calculate first derivative du by dr. Okay, so where it is a plus epsilon, it means r greater than a. So what is the wave function there? So here is what? Okay, so it is b sine of a r by delta. It is here a sine of a r. Clear? So now let's write what is this differentiation of that. So it is simply b. So it will be cos. So k will come out, cos of then k a. Got it? Okay, plus delta. It will be actually a plus epsilon, and we are taking epsilon tends to 0. Samajh aa? Then minus. So you are having a. So then it is again k cos of ka. It is differentiation. This one du by dr. This one r less than a. So it is cos of ka. Clear? So you put actually a minus epsilon. Epsilon is equal to 0. Okay. So it's equal to now twice m v naught by h cross square. So what is u of a? That means at a. So it is actually this thing, either sine of ka or sine of ka plus delta. So let me put it as, so some b sine of ka plus delta. Everybody followed it? Everybody followed it. So now how we eliminate a and b here? You just divide, let's say, divide equation second by equation first. Okay? Got it? So, or you figure out what is the ratio a by b and substitute it there. Can you do this step? Okay, good. Simply eliminate a and b, or divide second by equation first, we'll arrive at this thing. So, which implies then, so after eliminating, so let me write. So, anybody can guess? So it's like, okay. So it will be something k cot of ka plus delta, because it's cos. Cos divided by sine is like this, minus k cot of ka. It's equal to twice m v naught by h cross. Got it? So this is the equation. So simply eliminate. Just put b by a ratio. What is that? So put it there. Okay. So that means you have eliminated two constants, and you will arrive at this equation. Okay. So have you got it now? What is the prescription? How to solve a problem? Okay. Good. So now where is the delta? It's in this very object. So let me calculate this part of Ka plus delta. It's equal to twice m v naught by extra square. So there is a k, so it will come down like this thing plus part of k, because I have taken k common. So can anyone tell me what is cot in terms of cot of a plus b? What's it in terms of tan? So this is 1 minus tan of a, so that's k a, then tan of b, tan of delta, then so you are having tan of a plus tan of b, tan of delta. So that's equal to twice m v naught by extra square a. So it is cot of. Okay. So now you take this object on the other hand side, just cross multiply, then rearrange the terms with tan of delta, because I am interested in which term? Delta term. Clear? So this gives me like this, tan of delta. Okay, so you multiply it on this side, so it will be this entire object multiplied by this tan of delta, and you are having tan of Ka here, so it will be something twice m v naught by extra square k plus cot of Ka plus tan of Ka. Okay, so it's equal to minus twice m v naught by extra square k tan of. So we have got what? So let's write then tan of delta. So that's equal to minus twice m v naught by extra square k tan of. So then we'll use the approximations. Okay, first we'll write it like this. Twice m v naught by extra square k plus cot of Ka plus tan of. So this is your tan of delta. Okay. So now we have figured it out. So let's write then. Okay, what is the form here? So it's 1 by tan a. So it will be 1 plus tan square. Okay, can I write it in this way? Okay, so anybody can tell me what will be the form? So it will be something cosine of Ka plus sin of Ka plus sine of Ka divided by cosine of Ka. So what you are having? Cos square plus sine square, that's 1 divided by sine K. So that means it will be like this thing, minus twice mv naught by extra square K something sine square K, because you are having tan already here. Okay, divided by 1 plus twice m v naught by extra square K. Okay, sine of Ka cos. Clear? Huh? Huh? Because cos and cos in the numerator, it will cancel out. Look here, so it is multiplying this very term. Look, you are having sine A cos A, so it will multiply this term. Clear? So then you are having sine A sine Ka cos K, it will go in the numerator. It is tan. Tan is sine by cos. Cos and cos cancel. It is what? Sine square. Okay. So now let's rewrite it. So what is our this thing Ka? Since in the low energy domain, Ka is less than 1. So that means, so this object is what? It's approximately equal to that A square, A square. Okay. So what about this thing? So it is simply equal to Ka, and this is equal to 1. Clear? Everybody followed it? Clear? Okay. So So you are having therefore this tan of delta. So it is approximately equal to then. Okay, so let me write it minus twice m. You need to rearrange the terms. So V naught K A square by H cross square divided by 1 plus twice m V naught A by H cross square. I have taken actually K common because you are having here it is K square and in the denominator what it is? K. Okay. Got it?
Yes, sir.
So what you are having, which implies cot of delta, that's equal to 1 by tan of delta. So it's equal to minus 1 plus twice m v naught a by h. It is simply rearrangement. Just do it. So twice m v naught k a square, okay, divided by h plus. Why I have put cot of delta? Okay. So I want to figure out sine. Because what is the scattering cross section? It is proportional to sine square delta. Okay. So for that matter, I will figure out cosec square delta. So what that is? So I am having cosec square delta. That's equal to 1 plus cot square delta. So how much is that? You can write it. It's something 4 m square v naught square k square a raised power 4 divided by h raised power 4 plus, because it's 1 here, so you need to multiply it here. So it is, so just do it. It is twice m v k is square by h square. Okay, so because I have put 1, look here. So you are having 1. So cot, okay, so when I have to put 1 plus cot square, so you put the square of this thing, so then add 1. So it is 1 plus square of this thing. Because you are multiplying this on both the terms. So this is actually this term, and this term is the square, and square is in the denominator. Okay? Got it? So let's write now this. Okay, so we have figured out now cosec square. So then we'll little bit approximate again. So therefore our total scattered cross section is equal to 4 pi sine square, 4 pi by k square sine square delta. Okay, we are taking L equal to 0. Okay, so how much is that? It's 4 pi by k square sine square is what? 1 by cosec square delta. So it is 4 pi by k square. What's 1 by? So it is, let's write it. So it is twice mv naught k a square by h cross square. It's 1 by cosec. That means I have to invert it. Whole square divided by 4 m square v naught square a square a raised power 4 divided by h cross square plus 1 plus twice m v naught a by h cross square whole square. Okay, so now since k square a square is less than 1, got it? Okay. So you can expand this square. Okay, so now let's look at this thing. You can expand this. So it's 1 square plus square of this thing plus 4 times. So ultimately, okay, so that is let's write it. So it's something. Okay, so you are having k square here and k square here. It will cancel out. So it's 2 square, it is 4 and 4, 16. So let me write it. It is 16 pi m square v naught square a square divided by h cross square. Okay, divided by 1 plus, so it 1 square is 1 plus 4 m v naught a by h cross square plus 4 m square v naught by h cross square plus, let me write
m square v naught square.
huh? Where? So it's twice, 1 plus twice ab. Okay, so then you are having 4 m square v naught square a square divided by h cross raised by 4, okay, into 1 plus a square a square. So I have taken k square a square common. Okay, it is k square a raised by 4. It's k square A raised for 4. Got it? Because why I want it in this form? Because Ka is small. So this is a small quantity. It's less than 1. You can ignore it. Samajh aa? So it's look. Why I am putting it in the simple form. Huh? Okay. So you can simply write it. Okay. Sigma total, that's equal to 4 pi A square. So let me write it in this way. Okay, twice m v naught A by h cross square. Okay, divided by 1 plus twice m v naught A by h cross square. It is like this, 4 square. So this term and this term. Okay. So if you see, it is something to 4 pi A square into 1 divided by 1 plus. So if you divide, so it will be something h cross square divided by twice m v naught A whole square. Clear? Yes, sir? Yes. Got it? Okay. Now look here, why I have put it in, this is the final form. So if you are having a sphere, the scattering, classical scattering cross section is actually 4 pi A square. So if you take any low energy scattering due to a spherically symmetric potential, it will be always what? 4 pi A square. But this is actually the quantum effects. Huh? That's why I have put it in this way. Got it? So now if I put, let's say, V tends to infinity. Okay, or let's take, since quantum effects are proportional to h, clear? So let's put h tends to 0. So what that means? So you are having classical value back. Got it? Okay, that's why I have put it in this fashion. So these are two examples how to calculate low energy scattering. So we'll take one more example first. So later on, so I'll be giving you a general prescription. Okay, we'll be in the general form how to calculate the phase shifters. So how much time is remaining? 10:15. Okay, so we'll be having a quick